Let's more precisely describe depth-first traversal, or DFT. Many constructs from the spanning tree algorithm carry over to this lesson, but there are a few changes. The node contains the parent node value rather than the children, as follows. The root does not have a parent, so the root's parent is none. We are going to construct the tree using DFT. Let's begin with the functions that are used by the DFT algorithm. First, as with BFT, we look for neighbors of the current node. In fact, the process is exactly the same, so please see the spanning tree algorithm lesson for details. Then we filter out neighbors that are already in the tree. This process is also carried over from the spanning tree algorithm. Once we find the new neighbors, we create nodes with the neighbor values so that we can add them to the neighbor stack. Here are the properties that describe this process. Property 1. Nodes with values vals and parent p is equal to the output of the makeNodes function, where input values are vals, parent is p, and nodes are an empty stack. Property 2. Output of the makeNodes function, where input values are v, rest, parent is p, and nodes are ns, is equal to the output of the same function, where the input values are rest, parent is p, and nodes are node v, p, and ns. Property 3. Output of the makeNodes function, where input values are an empty stack, parent is p, and nodes are ns, is equal to ns. We first convert the operation to the makeNodes function call. Then for each neighbor value, we create a node with the parent and push it to the node stack. Let's try an example. Try using the properties above to prove that the nodes with values Milan, London, and parent Paris is equal to the stack with node London and Paris and node Milan and Paris. We're now ready to describe DFT. DFT is a recursive algorithm, which means we will describe one DFT operation in terms of another DFT operation. First, we will convert the DFT operation to a build DFT tree function call as follows. Spanning DFT tree of graph G starting from V is equal to the output of the build DFT tree function, where input graph is G, tree is an empty stack, and neighbor stack is a stack with one element, node V and none. The neighbor stack initially contains one node with value V. The following property describes the build DFT tree function call recursively. If children of the node top in graph G is equal to children, and elements of children that are not in tree T is equal to new LMs, and nodes with values new LMs and parent top is equal to final LMs, and the result of dumping final LMs to rest is equal to the new stack, then the output of the build DFT tree function, where input graph is G, tree is T, and neighbor stack is node top, parent, and the rest, is equal to the output of the same function, where the graph is still G, the tree is node top, parent, and T, and neighbor stack is new stack. The top node is moved from the neighbor stack to the tree, and the new children of top are pushed to the neighbor stack. For example, try using the property above to prove the following. If G is equal to pair Paris-Milan, Paris-London, Milan-Brussels, and Milan-Munich, then the output of the build DFT tree function, where input graph is G, tree is node Paris-None, and neighbor stack is node Milan-Paris and London-Paris, is equal to the output of the build DFT tree function, where input graph is G, tree is node Milan-Paris, Paris-None, and neighbor stack is node Brussels-Milan, node Munich-Milan, and node London-Paris. First, we can show that the children of the node Milan in graph G is equal to the stack Munich, Brussels, and Paris. Then we can prove that the elements of Munich, Brussels, and Paris that are not in tree node Paris none is equal to the stack Brussels and Munich. Next, we can show that nodes with values Brussels and Munich and parent Milan is equal to the stack node Munich with Milan and node Brussels with Milan. Finally, we claim that the result of dumping the stack with node Munich Milan, node Brussels Milan, to the stack node London Paris is equal to the stack node Brussels Milan, node Munich Milan, and node London Paris. We are finished when the neighbor stack is empty. In other words, output of the build DFT tree function where input graph is G, tree is T, and neighbor stack is empty is equal to T.